What about now? Yeah, let me confirm so that. Uh, okay, so we can start. I'm sure by now you should be able to see me and at the same time be able to get the voice. If you are able to get what I'm saying, just kindly type yes in capital letters. Then I'll be able to check because I'm seeing what you are typing. So just type yes if you are able to get what I'm saying and if you've logged in. All right, I'm seeing some students are saying yes, we are able to get you, so I think we can start. Whenever you are not able to get me, just be quick to mention so that I can pause a little bit and look at what could be the problem with the connection, okay? Remember we had a class in the morning and we are continuing from where we had stopped. We had started looking at the coordinate system. We had looked at the Cartesian plane. We had looked at the cylindrical plane. We had looked at the spherical coordinate system. And we had also moved on to look at the integration of some surfaces. We had looked at the line integral. We had also looked at the volume integral as well as the surface integral. So this afternoon, I would like us to continue from where we had stopped. And remember, when we just stopped, we were looking at some operators, which we mentioned that there are so many operators that we actually use in mathematics, the plus signs, the minus signs. You can mention there are so many, and specifically, I was just introducing to you what is called the del. So this del it's like an operator that operates on a function and it gives it results. Like I gave you an example in the morning of a plus sign where we said 2 plus 3 is equal to an answer somewhere here. This we said this is an operator. So this operator is going to operate on these two numbers, and in this case we know that this is a plus sign, which is an operator called plus. So this plus operates on the two numbers to give us the result, which is 5, as simple as that. In the same manner, the del that we introduced, or in other words, some call it delta, but some call it del, which we said has this symbol, also can operate on a function f, which on a function phi, which we say if, for example, this function phi, this is the same as this partial of x, that is if it is in the Cartesian plane of ax, then plus the partial of y of ay plus partial z az. So this is the operator. If, for example, like in the example that we had in the morning, this phi is given by an expression x, y, z, that is the function. So it means that we need to multiply the whole lot of this multiplied by x, y, z. So that in the end, what you get is as simple as, if you look at it, from here you don't even need to do a lot of mathematics. You know that if you get this first component and multiply it to this, what happens is that this x will come here and it will cancel this. So you remain with yz and this vector here. So straight away you have yz a as a vector plus this cancels the y there. When it comes here, this and this will cancel. Then you have the xz, then ay, then plus this will have the xy and az as a vector function. So that is what you have when that operator actually operates on this. And in other words, this is called the gradient of phi, which is defined as that, as simple as that. All right. Okay, so we continue from that where we had stopped, and let's look at some properties of this gradient. That is where we'll start from. So the properties of this operator that we are looking at. Now, let's look at some properties. Properties of the gradient. In other words, what we are saying is this is the gradient. You have to specify it. The gradient of, say, a scale. So immediately we take that as an example. So we take, let's look at an example and look at the properties. So we are saying, let V be equal to a scalar quantity. So here, a scalar quantity, what we mean are things like mass, for example. We have, in other words, you know that they are what are called the scalar quantities and they are what are called the vector quantities. So in a scalar only has magnitude, and this has magnitude and what? That is magnitude and direction. So what we are looking at is properties of a gradient of a scale. So we're just looking at a quantity, for example, that only has magnitude for a start, before we come to the one that has both magnitude and what? And direction. So put that in mind, that at the moment we are just focusing on this, the scalar quantity. Now, we have said that let V be equal to a scalar quantity. So we want to have our del so that it operates on this scalar quantity V. So what we have is that this V, it means that the gradient, we'll write it short. So it means that the del of V must be equal to, this is the same as the gradient of V, which is equal to a vector quantity. In other words, we remember that this del, in simplicity, is, if you remember very well, this is a vector. So if a vector is multiplying a scalar, what we get is a vector quantity. So now, the first thing that we need to note in terms of properties is that the magnitude of this gradient of V is equal to the maximum rate of change. That is the first thing that you need to note. Maximum rate of change. For example, if you have, maybe say, a function which is a line on your xy plane, so you want to find its gradient at that point. So immediately you can pick 2 points. From high school you've been doing this. So you pick 2 points which are going to put that point inside. Then you have 1 point there and another point there. So you have your, say your A1 there and your A2 here. Here you have X1, Y1, then you have Z1. And here you have X2, Y2, and Z2. So you use these 2 components to get your gradient. And that gives you your maximum rate of change. Now, number 2, the direction of this is actually along along the direction of the maximum, is along the direction of the maximum rate of change. As simple as that. Now, what we have is that here what it means is that first we have said that this magnitude is actually equal to the maximum rate of change. The rate of change, what this must remind you is, for example, the velocity. If you say your velocity is the rate of change of displacement with time, for example, your acceleration is, this is the rate of change of displacement over the change in time. Your acceleration is the rate of change of what? Of velocity over the change in what? In time. So that is what we are trying to say there. So this, the second point is actually telling us that this direction, the direction of this gradient is actually along the same rate of change of the function that we have been given. So we have two more points that have been given there, where it says this same function number 3 is actually at a point that is perpendicular to R, that is on the surface. So in any, that is point number 3. So we are saying number 3, the gradient of V at any point is actually perpendicular to the radius. So it's actually perpendicular, that is, which is to the constant, right? V, which is on the surface. In other words, the implication of this is that if we have a surface like this one, which is from the first example that we had, it means that the implication here is that in this case, what we have is that if you have the change, this is the surface that you have, so the change here will be in this direction. If you have, that is your, this is your y, this is your x, that is your z axis. So it means that what we have here is that the implication is that the gradient of v, which is the surface, this v, will be in this direction, which will be perpendicular to the surface here. That is the implication. All right. And the last one that we need to mention is that the projection of this gradient of our scalar quantity, which is a v, is actually in the direction of the vector, is in the direction of a unit vector, which is denoted by A with a small symbol on top there, and that is what we need to take note of. Like when we started looking at the unit vectors, I mentioned that if we pick one unit vector, for example, this is your y-axis. If you have one unit vector, this becomes a unit vector in your y-axis. And that is just to remind us that even this projection in that direction, actually that is projected in the direction where there is this unit vector A. Now, we move on to what is called the divergence of a vector. Right. So we have looked at the properties of the scalar. Now let's see what is known as the divergence of a vector. All right. So we look at what is called the divergence. That is the divergence of a vector. In other words, remember, the one that we're looking at is actually a scalar. Seems I have a bit of some challenge with this picture. All right, sorry for that small disturbance. It seems I had a challenge with the picture. I was checking what you are able to see on your side, and I noticed that the video had stopped at some point. All right, I was saying that we continue, we look at the divergence of the vector. So what we are saying is that this actually is defined as the dot product. This dot product of an operator. So in this case, our operator is what we are calling the del, and a vector which is B, then we define this. This is like the dot product, which is defined as del dot B. This must be equal to the divergence of a vector. As simple as that. Now, let's now take this B as an example. If we say the vector B is equal to Bx, that is the magnitude of the vector B in the x direction, and multiplied by the unit vector Ax, then plus the magnitude of the vector B in the y direction multiplied by Ay, which is a unit vector in the y direction, and then plus Bz, that is the magnitude of the vector B in the z direction multiplied by the unit vector Az. Now, this means then what we have is that the dot product, which is the divergence of the vector B, must be defined as del dot B, that is the delta of B, must be equal to the partial derivative with respect to x of Ax, that is multiplied by the unit vector Ax. Then we add that to the partial derivative with respect to y of Ay plus the partial derivative with respect to z of Az. Then all this operator, we multiply it, we dot it to Bx Ax plus By Ay plus Bz Az in that way. Now, from here, like remember what we are done when we are finding the gradient of a vector. This time around we are finding the dot product. So when you do this, at the end, the implication here is that del, that is dot B, must be equal to the partial derivative with respect to x of Bx plus partial y of By plus partial z that is the final solution for that example. All right. Now, this is in an event where B is just a vector. What happens if we have an example where we have this as a vector field? So let's look at that example. So the other example that we can look at is, we say, let A be equal to a vector field. All right. So that means for our solution, the divergence of A, which is the same as the delta dot N, this must be equal to the limit as this change in V approaches 0 of our integral, which is the surface integral, that is A dot ds over the change in the volume. So that is how we get the divergence of a vector field, as simple as that. All right. The rest is just for your information that you have in those notes. So we move on. We move on to what is called the divergence theorem, which is very important. All right. So, divergence theorem. When you are asked to prove, you may be asked in an exam or in a text to say you prove the divergence theorem. How you prove the divergence theorem is what we are going to do here. So, you may be asked to say, prove the divergence theorem, as simple as that. And you may not see any kind of an equation given to you or any kind of a diagram given to you. So you must be able to actually prove this. Now, what this means is that, let's look at the surface integral. Okay, so we look at the surface integral, right? Where I remember very well in the first example that we had, this was the surface which I had introduced you to. Then we had tried to cut it into small surfaces, which we were calling the ds. So the implication is that from this point to this point, we're calling this ds. Then, remember very well, we had the total surface was given by ds1, ds1, that is ds2 dot up to dsn. That is the number of the surface segments that we've actually made. Now, in this case, we are saying let A be the total outward flux of the vector right? Of the vector through the surface. Alright. Okay. That means that means what we have as our total surface integral, remember when you see its symbol, the integration plus this surface on top, then there's an S down there. It means that this is the surface integral that we're talking about. The line integral does not have this circle on middle. So what we have is that this is A, the S in that way, and this gives us, we are integrating the volume, which is the divergence of A, which is dot V. Remember what I'm putting here is the divergence theorem. Then from here we have to prove it. That is what is very, very important. So this is equal to that, which implies that the surface integral of A ds, this must be equal to the volume integral of the divergence of A, which must be multiplied by dv. Okay? In other words, we are moving from the surface to the volume integral. That is what we are doing. That is what is all about the divergence theorem. So the implication here is that the double integral of A ds must be equal to the triple integral of the divergence of A dot dv. In other words, if we have to come back to the surface, for example, what we are trying to explain here is where we have the distance, where we have the velocity, and where we have the acceleration. This is what we're trying to explain. So in order for you to move from here to come to the velocity, you have to differentiate, isn't it? You have to differentiate. And for you to move up to there, it means that, again, you have to differentiate this. Now, in order for you to move from acceleration to velocity, you have to integrate. And for you to move from velocity to distance, which is just like the displacement, again, you need to do what? To integrate. That means, for you now to move direct from here to there, it means that from acceleration to the distance, you need to have this double integral. That is what takes you to the triple integral of the volume, as simple as that. Okay. So, what we say here, what we need to note now, is that this theorem is the one that relates surface integral to the volume integral. All right. Okay, so in other words, what we are saying is that this implies that the triple integral of the divergence of A dot V must be equal to the double integral of A dot S. This is very important. So, in an exam, this is the only thing that you could be given. In a test or an exam, to say you have to prove this equation. Prove that this left-hand side is actually equal to the right-hand side. In other words, you must prove that the volume integral of a given object is the same as the surface integral of that same. The triple integral of the volume of that surface that will be given is the same as the double integral of its surface integral. So you have to prove that, and we are going to do that together. So this is the example that I'm going to take you through, and we'll move slowly but sure. Then from there we can go to the curl of a vector. All right. So let's prove that together, so that when you are alone, you are able to go through it, and then you are able to reproduce it and prove the theorem. All right, let's look at the proof together. So, when you are trying to prove a theorem in an examination, it's advisable that you have your diagram nearby. Put it in diagram form, because diagrams are easy for even the one who is looking at your work to understand what you are trying to say. So put your diagram, make your assumptions. After you make your assumptions, put your diagram to support your assumptions. Then from there now you can start your derivation and prove what you want to prove. Okay? Now, the first thing you need to do is to put your assumptions. So we are saying, let us consider that is a volume which we are calling V, which is kept in the vector field, which is A. So you should look at this vector field A as an electric field, where we have a volume which, or in other words, you have say a box which has volume V, which has been placed in a vector field or an electric field that is of strength A. That is how we look at it. So meaning, the simplest way to do it is, we have our box which is here. So that is our small volume, like that. We know that this side, if you check this side, this is what is going to give you the Z. That is in the Z direction. If you want to put your XY axis here, you realize that this is your Z axis, this is your X axis, and this is your Y axis. So if you look at this box, you realize that this component is what we shall call the Z, which is in this Z direction. Then, the other component, which is this, from here up to there, this we shall call it the X here. This is the X. Then, this other component here, we shall call it the Y. Are we together? Yes. Now, what we need now is to have, if you bring down these components to the Y-axis, the implication here is that this becomes your X1, that becomes your X2, and this whole surface which is here, where this component is being held, that becomes your volume, which you are calling V. Right. Now, okay, in fact, that must be your X, this must be y, which is going in this direction. All right. Okay, now, okay. So, what we want is we have this volume that this box is occupying. So we want to pick one component of that. Remember when we were looking at the surface integral, we want to get the surface, one part of the surface where this is occupying, this box is occupying in this vector field A. We cut one small piece, which we are calling the ds. Then from there we can make some integrals in order for us to arrive to our derivation. So what do we do? The first thing is, so we are saying, looking from the x direction, x-axis, which is the direction, we have, right? We have a small area. This is a small area which we are calling dsx in that way. So this is defined as dy dz because it is in the x direction. When we want to define it, it has one component in the y and the other component is in the z direction. So the product of the two must give you that small surface. What are we saying here? If you have like this is your x, this is your y, and that is your z axis, it means that if you are looking from the x direction, what you are able to see in that box, you are only able to see this z direction as well as the dy direction. Because you are looking from this side, you are just seeing this surface here. That's where your eye is pointing. So you are just able to see one side. If you are looking from this is what we are calling the x direction. So you can only be able to see the components in the z and in the y direction. That's why that small component, the x, must be given by the y dz. As simple as that. Now, we want to see what we get when we look at now the divergence of A. We know we have this small surface that we have cut, which is giving us ds of x must be equal to dy equal to dz, like that. Now, the divergence of A, which is equal to, remember from our previous definition, we had written this as del of A. This must be equal to, we now have to write this in full, which is partial with respect to x, partial, and then we multiply that with x plus partial over partial y in the y direction. We multiply that by the vector in the y direction, then plus partial over partial z in the z direction, right? Then this must be multiplied by a, which is the component of the vector field in the x direction, multiplied by ax plus ay multiplied by ay plus az multiplied by az in that direction. Alright, so these are unit vectors. Don't forget to put them the way they're supposed to be. Now, after we've done that, this implies that what we get now is that the divergence of A must be equal to partial over partial x, ax, plus partial over partial y, ay, plus partial with respect to z of a z. That is what we get. Now, from here, immediately what you do is you introduce the integral signs. So from here you introduce triple integral on the left side. So what we are saying is not. So introducing the triple integral on both sides, we get the following. So what we have is that the triple integral of the divergence of A dot dv must be equal to the triple integral of partial x of ax into partial with respect to y of ay, right? That is ay plus partial over partial z of az, right? This gives us dv. Now, this is the left-hand side. If you look at this component, we have it in the equation that we are trying to prove. Remember, the equation that we are trying to prove, which is the divergence theorem, states that what we have is that, if you remember very well, we had said we are proving that the double integral of A dot ds must be equal to the triple integral of the divergence of A into dv. So if you look at this, this is what we are proving. This is the same as that. If you look at it. So in other words, the right-hand side of this equation, so we are saying the right-hand side is equal to the left-hand side. So we are saying that the right-hand side of this equation is equal to the left-hand side of this equation. It means that the right hand of this equation must be equal to the left hand of this equation. And that is our work that we're supposed to prove. We must prove that the right-hand side, this right-hand side, can be reduced to this. That is one thing that we need to prove when we are done. Right. Okay, so we continue from there. All right, so now we have seen that actually the triple integral of the divergence of A dot v is equal to the triple integral of partial x of ax plus partial y of ay plus partial z of az. So this is what we are able to get, and this is with respect to dv. Now, straight away, we know that this one we already have it. So we need now to reduce the right-hand side. So this is equal to, we have to now expand it. And then what we find is that this is our x of ax plus, that is our y of ay plus our z there of az. Then this now is given by, this is dv. You know that volume is equal to LBH, so which is the same as xyz. So dv must be equal to dx, dy, dz. As simple as that. That's why we are able to get dx, dy, dz at that end. So this is just the same as that. Right. Then from there, I will not go through all the steps. I think it is clear from there. What you are able to see, I will just go to the other stage where we have done the first integral, and then we are now at the second integral of ax into dy dz plus ay into dx dz, then plus az into dx dy. So this is where we are. From here straight away, what we have is that these two, remember where we started from. I mentioned that the sx must be equal to dx dz, meaning the xy must be equal to the x. See that? This is the y dz. This must be equal to the x dz, and then the x z must be equal to the y, must be equal to the x, then the y. So that is very critical, and that is what we are going to use at this next stage. So immediately, what we see from here is that this is our x, the sx, this is nothing but our dsy, this is nothing but our dsz. So immediately we make that substitution, and what we get is that we have ax into the sx plus ay into the sy plus az into the sz, right? So immediately what we see is that we have now to factor out these a components and multiply them to a vector. So immediately there we have ax into a small vector, which is a unit vector, ax plus ay into unit vector ay plus az multiplied by the unit vector az. Remember, this is a unit vector that we are introducing. It's just the same as multiplying a number by 1. So multiplying a unit vector to a vector does not change it. You just introduce it because it is a unit vector. Right? Then this we are multiplying into the sx of ax plus the sy of ay plus the sz of az. Right, just like that. Then immediately what we see is that what we have down here is actually nothing but the integral of a into s. If you look at this component here up to there, this is nothing but a. This component, the whole lot of this is nothing but vector a. If you look at this, the whole lot of this is nothing but the s, as simple as that. So immediately you see that this is a, the s. And then from there, you just push it on top here. You say, this, we have proved that actually it is the same as the double integral of a into the s, and they proved it as simple as that. So, hence, proved. All right. Okay, so let's look at what is called the curl of a vector. We have to continue from there. So we're saying, let's look at what is called the curl. So let A be a vector such that the curl of A, which is the same as the del cross A, must be equal to the limit as the change in the displacement goes to 0 of the surface integral of A into the L over the change in S multiplied by the small vector. In other words, if we have the electric field moving in this direction, that is your A, then you have your change, which is a small surface, this surface here. That means this is your unit vector in this direction. So this is your path integral, which is your curl, in other words. Right, and then basically that is what you need to know. And this is the crucial part that you need to know about the curl. And that is done. I will not talk too much about the Stokes theorem. You have just to go through it and see if you have any challenges there. Okay, maybe just something for you to understand is that the Stokes theorem is actually trying to prove, like the one that we just like the one that we're looking at, the divergence theorem. So that is basically what the Stokes theorem is talking about. So I'll just put it up here for your information, but it's just the same as this. You just need to know that the curl of a vector actually is given by the divergence cross A. This is not a multiplication, this is a cross product. So take note of that. All right. So this is the Stokes theorem, and I will not prove it because we have gone through that with the other one.